Given a dual paned glass window with each pane of 1 centimeter thick glass, a half a centimeter thick airspace between the panes, and having the shape of a perfect square with 50 centimeters length on each side, what is the resistance to heat flow for this window, given that the glass has a thermal conductivity of 0.96 watts per meter Kelvin and the air has a thermal conductivity of 0.0262 watts per meter Kelvin? And then once we have that, it should be pretty easy for us to calculate what the rate of heat flow would be if the outside temperature is 4 degrees Celsius and the inside temperature is 21 degrees Celsius. So the way I'd like to look at this, let me kind of draw. We're talking about a dual paned window here, right? So it's got the two layers of glass. So maybe I'll just draw like that right there. And then there's a little half the width of that space between the two of them. So I'm thinking about like this being glass. This is glass, and maybe I'll put an A there for that is air, and hopefully that kind of makes sense. Now, in terms of resistance to heat flow, heat conduction, we said was delta T is equal to the thermal resistance to heat flow. I've called it R sub T, R for resistance T, to make sure it's thermal, or I guess you don't necessarily need it, but there is also a thing called electrical resistance, so I put it there so that I don't get confused with that, but we're not doing that in this class, so in that sense, maybe it's only a confusion for me. And then that's multiplied by the actual rate of heat flow in terms of heat per time. And what we saw in the previous example was that the correct formula for the resistance to heat flow was this one, where D was kind of the thickness, or if it was a long rod type thing, the length perhaps. Maybe it makes more sense as a thickness actually for glass the way we're doing it here, divided by thermal conductivity multiplied by cross-sectional area, which in this case was the area of the window pane. However, in this case, we have a dual paned glass window, so there's multiple layers. So one way to think about this is to say there's going to be a resistance for one of the glass panes. There's going to be a resistance to heat flow for the air as well. And then there will be another thermal resistance for the other glass plane. Not gas, right? Glass isn't really a gas. Air is, though. And so I've kind of subdivided this into these three. And so maybe what I should just do is calculate what those three are. And conceptually, it makes sense to me that the overall resistance to heat flow should maybe be the sum of those three. And I'm just going to tell you that that is true. Actually, it's not something I've bothered to try to prove mathematically in these examples, partly because it's kind of annoying. If you want to try to do it, though, it's feel free to check it out. But it definitely, I think it makes sense that if you add more layers, that adds to the overall resistance to heat flow. So the resistance to heat flow for the first pane of glass is actually going to be equal to the other pane of glass, right? So in that sense, the way I've symbolized this here, resistance to heat flow 1 is equal to resistance to heat flow 3, and those would be equal to the thickness, maybe I'll put a little sub G here for the glass, divided by the heat conductivity for the glass, and the cross-sectional area is the same for everything here, so I don't think I need to subscript that. In terms of numbers, though, this would be 0.01 meters. That corresponds to the 1 centimeter thickness of the glass. For the thermal conductivity, we'll use the 0.96 that we're given. That was the same as in the last example, watts per meter Kelvin. And then multiplied by, we'll use 0.5 meters for the one side of that square-shaped window, and then square that to find the area there. And I guess I need to elongate that a little bit. And in my calculator, the number that I get for this part, for this result, is 0.041, and then it's like 6 repeating. Maybe I could just write it as 0.0417. And I think we saw last time this was kelvins per watt was the appropriate unit for this. And then we're going to want to sum all these up once we're done, but I need to find the resistance to heat flow for the air part. So that was RT2. And so for that one, I'm going to use the thickness of the air gap in the window pane, the thermal conductivity of air, and we'll use the same area of that trapped air between the two panes. So the thickness was 1/2 a centimeter, which in meters would be 0.005 meters. And then the thermal conductivity is a smaller number here, which is going to lead to a larger resistance, right? Because we're dividing by a small number in this expression. So that should lead to a relatively large resistance here, which is actually kind of the thing that we want, because dual pane windows are supposed to be more insulative, so they should resist heat flow through them. And the area, again, we'll use is 0.5 meters. Square that, and now it's time to go get a calculating device again. My calculating device says for this 0.7633587786 and so on, or at least that's as far as it goes actually, but I think I'll just say 0.763 kelvins per watt. And then if I want to know, like, well, what is the total resistance, because that's the thing I'm asked for in the first part of this question, is the total resistance. I'm just going to add up all three, but really that means I'm going to add twice, right? It would be equal to 2 times what I got for the first one, because the third one is really the same as that, plus the part for the air. And so I put that into my calculator actually without rounding, but I get I get 0.847 perhaps. Actually, I guess when I check with the slide, it might round a little bit further, I'm thinking, because it looks like a lot of things here are at only 2 significant figures, so I suspect that's what's going to happen. But we'll see that they align with each other. And then if I want to find the rate of heat flow, that's Q over delta T. So I just divide, right? So if I want to find that, this is what I'm going to do, right? Q over delta T is equal to the other delta T. So we got to be careful. There's delta T for time, but we're calculating this whole thing. We're not finding any individual components of that. We're just taking the temperature difference, divide by this overall resistance to heat flow. And when you put that in the calculator, that was like 17 divided by this number, and my calculator, it rounds off to about 20 watts, which is actually like 20.07, etc. But 20 watts is probably good enough for this question. So those two numbers I can now check with the slide and see if that all turned out correct. And yeah, it looks like within rounding, because this probably should have been rounded to 2 sig figs, as I said. Interesting to note that for the single pane window, it was 204 watts. This is 20 watts, right? That's like at least a factor of 10 improvement there. So that's amazing what dual paned windows can do for you.